So let's talk about time scales. This is a log scale. Each tick on this chart is 10 times to the value to the one left of it. I've got nanoseconds at the far left and millions of years at the far right. Now, normally when we talk about time in software, we're talking about the far left side of this chart, because computers are fast. Processor and memory operations, they're measured in nanoseconds, disk and network in milliseconds. If a computer takes a second to do something, we start getting impatient. Now, this middle of the chart is human scale time. We have our threshold for perceiving, like one event was before the other, is around 100 milliseconds. Our lifespan is around 100 years. But we can also talk about software at this scale too, because software is by and for people after all. We track work in terms of hours and days and weeks, and product life cycles in terms of months and years. Right about here, this red arrow, that's about how often there's a new JavaScript library we're expected to have an opinion about. With this arrow here, this is how long we've had computers. My grandparents are older than that. In terms of human endeavors, software is a profoundly young field. I mean, even if we stretch the definition of what makes a computer, what makes software to have Lovelace and Babbage, then it's only a little bit over to the right. That's longer than any human who's been alive, and actually longer than the city's been incorporated. But those trees outside, those are older than software. Because software is such a young field, we don't really think about this right side of the scale here at all. Years, decades, centuries, and so on. I mean, I understand why it seems impossible to even conceive of software in those time scales when computers advance so quickly. But I think this is a mistake. As web developers, we tend to think of anything older than 6 months as legacy code. But there is a ton of code from the 60s and 70s that is still running today, and the design decisions that were made back then are still reflected in contemporary systems. There's no reason to believe that software can't live for 50, 100, even 1,000 years. Anyone in this room could be working on a project that has that kind of lasting impact. So first, let's talk about bit rot and the paradox of software decay. Now, physical artifacts, things fall apart. Wood rots, plastic cracks, metal rusts, parts wear out or break and need to be replaced. Machines demand maintenance. This does not actually happen in software. Aside from cosmic rays, bits do not actually rot. A function will not wear out no matter how many times you call it. And computers can break, but software is just information. Software can be eternal. And on the other hand, there are all sorts of circumstances where software will stop working. This happens all the time on the web because everything is so interdependent. Links break, servers crash, Twitter buys a third-party API service and shuts it down 30 minutes later. That actually happened this week. This is a huge point with IoT devices. Your smart home system, the thing itself still works fine, but the service has been shut down and now it's totally useless. And even if your web app is totally self-contained, it still depends on your user's browser and computer, and that can break your software too. So much of what we do in JavaScript, I don't know why my slides are lagging so far behind. JavaScript has suffered so much to remain fully backwards compatible with mistakes Brendan and Ike made back in the early 90s. So some of you probably remember Smushgate from a few months ago. There was this whole controversy about how adding a flattened method to arrays would actually break websites that use this 8-year-old version of MooTools. Rule 0 for adding any new browser feature is don't break the web. That said, browser vendors break the web all the time. If you think about it, the whole point of new security features and ad blockers is to break people's software. The hope is that you're breaking bad software, but it is still breakage nonetheless. And the shift to mobile over the last 10 years, that broke a lot of software. It's really quite impressive that the early mobile web experience worked at all. Frankly, in a lot of ways, I'm grateful for this. I got started in around 2010, and a lot of my work when I was getting started was making websites mobile-friendly with media queries and rewriting Flash stuff in JavaScript. But on the other hand, it's hard to feel good about anything that prevents people from seeing Homestar Runner cartoons. Great. Software is information, and information can live forever. But doing anything with information, extracting meaning from data, it's wholly dependent on context. You cannot make sense of a message if you don't speak the language, or if the message presumes background knowledge you don't have. This tablet is written in the language of ancient Crete. We don't know what it says because nobody can decipher this language linear A. We can preserve this tablet forever, but we cannot do anything with this information. And likewise, you can't do anything with software if it presumes things about the computer it's running on or the network it's connected with that are no longer true. You can preserve data forever without it ever changing, but preserving meaning requires continuous change. Uh-oh. Very dramatic. Now, preserving software requires continuous adaptation to shifting contexts. So what does this look like? Now, there's a book about architecture that shaped a lot of my thinking around legacy software called How Buildings Learn. And it's about the qualities that are present in unremarkable industrial buildings that nevertheless make them valuable and useful for tens to hundreds of years. Now, like software, buildings need to evolve over time if they're to remain useful, because buildings require physical maintenance, of course, but buildings also have the problems of shifting context that we encounter in software. As time passes, people come to expect, running water, electricity, air conditioning, Wi-Fi. Just as many of us will probably spend a lot of time working on GDPR compliance, people who worked on buildings have to deal with ADA compliance. Manufacturing leaves town, and the old textile factory turns into the Loom, a hipster mall with loft apartments. This is right outside my neighborhood in Brooklyn. I don't want to lean too far into this metaphor. I'm not suggesting that you repurpose old insurance software into luxury condos. But the idea is from this book that has served me well in dealing with legacy software is this notion of shearing layers. Because most buildings are not monoliths. They are a network of interconnected but still discrete systems. The idea is, some parts of the system rarely change. It's not impossible to move a building, but it rarely happens. Location is a pretty fundamental property of a building. On the other hand, some parts change all the time. Furniture it's meant to be moved around and reconfigured and replaced. And then in between this, you have other systems and structures, like interior walls and HVAC don't get moved around every day, but they're not intended to last forever. They're understood to be impermanent. Exterior facades are exposed to the elements, and they need to be replaced periodically. But this doesn't mean you have to actually change the walls themselves. The structure of the building, the foundation, in those load-bearing walls, they last a lot longer than the other parts, and also because they're far more expensive to replace, they don't need to be changed nearly as often as anything else does. Now, the key to longevity is that these systems are mostly independent. You can move furniture around without knocking down walls and vice versa. In the software architecture, we have a lot of equivalent ideas, like hexagonal architecture, domain-driven design, or high cohesion and low coupling. A lot of this you'll see in object-oriented literature, although a lot of that hasn't really made it to JavaScript. But there are dozens of talks on this topic, and I only have 3 minutes left. So instead, I'm going to talk more about what this looks like on a decade-long time scale. Now, one of the oldest programming languages still in use is COBOL, the Common Business-Oriented Language. I think there is one person here who has written COBOL professionally?
Yeah.
Oh, there are multiple. This is incredible. Oh, I'll have to talk to you afterwards. Sorry, this section may be traumatic. So the idea is that business-oriented in this case means the math features are built for accounting and not science, and there's a lot of built-in support for processing text and database records, or at least a lot by 1960s standards. Most importantly, it was designed to be readable, if not necessarily writable, by non-programmers. Like many efforts to make programming accessible to non-programmers, it was not successful, but it seems like it was probably an improvement over machine code. Now, COBOL is not a well-liked language. Now, here's the jargon file entry on COBOL. I just want to emphasize this line. No self-respecting hacker will ever admit to having learned the language. Its very name is seldom uttered without ritual expressions of disgust or horror. Ritual expressions. I mean, contempt culture has been with us for a long, long time. But here are some facts about COBOL. It was the most used language in the world for at least 20 years. A huge amount of COBOL software is still in use, particularly in critical infrastructure. The oldest software still running today is written in COBOL, and there are people who are entering the industry now who are still writing it. So the oldest continually running program is MOCAS, short for Mechanization of Contract Administration Services. It's used by the Department of Defense for tracking contracts and vendor payments. It was originally written in 1958 in COBOL's predecessor language, Flowmatic, and then ported to COBOL a few years later. Now, of course, it's changed a lot since 1958. I mean, just think about the changes in hardware since then. The computers being used in 1958 mostly had vacuum tubes instead of transistors. In many cases, computers weren't used interactively. Adding a contractor running reports on the system probably involved feeding a stack of punch cards into the computer and getting a printout the following day. At some point in the 70s, it was, well, by 70s standards, modernized to be used interactively with these green screen terminals. The user interface of the program was changed completely, but the core business logic remained more or less the same. And the system continued to adapt throughout the 80s and 90s and aughts and even today. Now, nowadays, to Mocha, to its end users, looks like a typical corporate intranet application. You access it through desktop PCs. You can even attach Word documents and Excel spreadsheets, because that's how people do military contracts today. But it is recognizably the same program now as it was in 1958. It is still essentially a CRUD app for managing invoices. And the Department of Defense has tried many times to replace this system wholesale with something new, but it is shockingly hard to justify throwing out something that works and has worked for like 60 years, even if it's archaic. It works well enough for its given task, and at any given moment, it's faster and cheaper to just hack in the next feature instead of starting over from scratch. As long as IBM keeps selling them hardware that can run it, Mochas will keep processing contracts. Now, I think there's a lot of parallels between COBOL and JavaScript. Every mean thing that people say about JS today was said about COBOL 40 years ago. In both cases, a lot of it is accurate. But just as COBOL ran on every machine and mini computer back then, JavaScript runs on every computer of any size today. Likewise, I think we can expect JavaScript to have a similar lifespan. Even if every new project from here on out is written in Elm or whatever, there's still going to be a massive amount of JavaScript code out there today that will, stick around as long as it is cheaper to hack in an update than rewrite from scratch. So, where do things go wrong in legacy software? Now, we talked a little bit about layers and boundaries, and a lot of the problems we encounter on the months to years time scale are violations of these. View code that talks directly to the database, that sort of thing. Now, we struggle with this, but this is at least well explored in our pop culture. We hopefully know when we're painting ourselves into a corner. Well, hopefully. The problems that really catch us off guard happen on the decade plus scale. Now, there is something in programmer psychology that makes us think that any short-sighted decision we make today will be cleaned up before it becomes a crisis. All evidence that shows that this is not true. Now, earlier this evening, Mickey showed us some nightmare security fix me using production code. Here are some to-dos from the source code that ran the Apollo 11 guidance computer. Now, the canonical example of short-sightedness is the Y2K bug. Now, in the 70s, it was common to store dates in a format where the year was represented as just the last two digits. When every byte counts, this apparently made a big difference. But even back then, people knew this would eventually be a problem. The COBOL style guide from 1970 warned programmers to use 4-digit dates. But people ignored this. They figured somebody else would come around and fix it before it became an issue. This continued until 1997, when it dawned on us that somebody else was us. Raise your hand if you were the person who did this. Now, a bunch of the programmers who had originally written the software back in the day found themselves put back to work updating systems to use 4-digit date representations and apparently charging outrageous consulting rates. But we've only kicked the can down the road a few years. Unix timestamps are 32-bit signed integers and will roll over in the year 2038. We have 64-bit timestamps in most languages and libraries today, which, but there's still a lot of code out there that's using 32-bit timestamps, especially on embedded devices. The smallest, most important devices that are all over the place and never get updated. Now, there's a couple of minor 30-bit integer bugs that, they're not, they did not halt society, but they've already bitten us when we really should have known better. A few years ago, YouTube's play count for size Gangnam Style rolled over into negative numbers because they went over 2 billion plays. And I've seen a couple of services go down for hours or days because they used 32-bit integers for database IDs and ran out of space. I think Pinboard was the last one that springs to mind. Yeah. A lot of import users here. Maybe 2 billion is an inconceivably large number for a human to think about on human scale things, but it is way closer than you think. But the more insidious data modeling bugs are I'm sorry, I'm going way over time. The more insidious data modeling bugs are the assumptions we make about how society operates and will operate in the future. So just while I was working on this talk, I noticed something in this code stuck out at me. Here's the full body of that program. Now, this is just demo code for explaining how to do multiple clauses and conditionals, but look at just how many assumptions about how society is governed are encoded in this short block of code. Like the age of a majority will always be 18, and the human gender is represented as M or F. Anything else is literally invalid. Now, maybe you're willing to cut 40-year-old demo code some slack, so here's a real-world example with those same assumptions baked in. I wrote this code. This is a dashboard that my team made for showing demographic data. I mean, it's not like I don't know any better. It's not like BuzzFeed doesn't know any better. I bet they know better at Quantcast. I mean, non-binary gender is legally recognized in many parts of the US, including this state, meaning some old-ass code got updated to accommodate it, but the infrastructure used by advertisers and publishers apparently has no place for it. This code is barely a month old, and it is already legacy. It is already outdated. So, the title of this talk, 100 Years of JavaScript, it is partly intended to read as a threat. But I'd also frame it as a responsibility, as a call to action. Now, on one hand, it's deeply optimistic to think that any of our code will matter in the long run. There are days that I wonder if I should be preparing for a very different world. I wonder if I should forget about JavaScript fatigue and learn how to fix small engines and radios. But on the other hand, I understand that I have put something into the world, and I am responsible for its impact, no matter how long that may be. Now, a lot of programmers are just now coming to terms with the ethical implications of how our software is being used. Or they look at the rise of Bitcoin mining and think about, like, oh, the direct ecological impact that software can have. But we also need to think about the longer term scale, not just how big our impact is in space, but how big our impact is in time. What are we leaving for future generations? Will that to-do comment still be in the code a decade from now? Will we have to come out of retirement to fix the equivalent of Y2K bugs? What invisible assumptions and bigotries are we encoding into our software that will be laid bare in a more enlightened time? Now, I've come to think of software less like manufacturing widgets and I guess more like forestry. Everything we do is interconnected, and the processes we begin today, they may not reach their conclusion for 100 years. Now, this is an awesome responsibility, but it's also an opportunity to shape the world far beyond our own lifespans. Make your immortality count. Thank you.